In this section, we're going to look at a couple of power series. The first one is for log of 1 plus x and near the base point 0. So x is 0. Let's set f of x equal to log of 1 plus x just because it's easier to write derivatives for f. And of course the value of f at 0 is log of 1, which is 0. So the constant term in the series is going to be 0. Then if we differentiate k times, we get minus 1 to the k minus 1 factorial times 1 plus x to the minus k. Let's just make sure that we believe this. The derivative of log of 1 plus x is 1 over 1 plus x times 1, so just 1 over 1 plus x. And that is 1 plus x to the minus 1. And when k is equal to 1, 1 minus 1 is 0, minus 1 to the 0 is 1, and 0 factorial is by definition 0. Anyway, so that's correct. Now, each time we differentiate, we're going to get another factor coming out of the exponent, and so there's going to be a minus sign, and there's going to be a k, and the exponent is going to drop by 1 from minus k to minus k minus 1, and or minus the quantity k plus 1. And you can see that this pattern is correct. Okay, so let's evaluate this derivative at x equal to 0. We get 1 to the minus k, which is 1. We get minus 1 to the k minus 1 and k minus 1 factorial. If we divide that by k factorial, k minus 1 factorial over k factorial is 1 over k, and minus 1 to the k minus 1 is minus 1 to the k minus 1. So that is the coefficient of the kth power of x near 0. X minus 0 is just x. And so we get minus 1 to the k minus 1 over k, that is the coefficient, and we have x to the k. Now if we examine this series just to ask ourselves, when does this series actually produce a number, then this series is convergent when the absolute value of x is less than 1. So its radius of convergence is 1. And of course it's an alternating series if x is positive. So when x is equal to 1, this actually converges. And it is the harmonic series if x is negative, because we'll get minus something to the k. And so when x is minus 1, this actually diverges. But anyway, that's a full discussion of this series. Our second example of a power series here will be a power series for sine x squared near x equal to 0. We know the power series for sine of x, but squaring that series is pretty awkward because it has very many terms. So let's look at it directly from what we know about Taylor series. F at 0 is 0, sine of 0 is 0, so squaring that gives 0. If we take the derivative of f with respect to x, we get 2 sine of x times the derivative of sine, which is cosine. And now it's actually very convenient to notice that 2 sine of x cosine of x is actually sine of 2x. And so now that's going to be a lot easier to differentiate than this product. So here we go, the second derivative. The derivative of sine is cosine, and the derivative of 2x with respect to x is 2. The third derivative, we're going to have the derivative of cosine, which is minus sine, and then another factor of 2 from the 2x being differentiated. We wind up with minus 4 sine 2x. I think we're ready to look at a pattern here because we know that every time that cosine is differentiated twice, we're going to get cosine again. And so when we differentiate 2k times, we differentiate twice k k times. Every time we differentiate, we get a factor of 2. So if we differentiate 2k times, we get a factor of 4. Every 2 times we differentiate, we get a factor of -1. And we're back to cosine. For the odd derivatives, we'll look at f prime, which is sine 2x. And again, every 2 times we differentiate, we're going to get a factor of 4. We're going to get a minus sign, and we're going to get back to sine of 2x. We'll write that down next. The derivatives from 3 on, so k here is 1, 2, etc. The third derivative is going to be sine 2x again with a minus sign because we've differentiated twice since we had sine 2x, and with a factor of 4, or 2 to the 2k, because we get a factor of 2 twice. And now if we look at the base point, the value of the odd derivatives at 0 is something multiplying sine of 0, which is 0. And the value at the even derivatives is cosine of 0 is 1 times this coefficient. So we get 2 to the 2k minus 1 times minus 1 to the k minus 1 for the even derivatives. And the series involves only even terms, x to the 2k divided by 2k factorial, right? This is the 2kth derivative. And then, of course, the minus 1 to the k minus 1 and the 2 to the 2k minus 1. If you want to think about convergence for this series, think about the ratio test. When you take the ratio of 2 successive terms, you're going to get an x squared. You're going to get 2 to the 2, or 4. You're going to get the absolute value of minus 1 to the k minus 1. It doesn't matter. So that's just 1. And in the denominator, you'll have increased k by 1. So you'll get 2k plus 1 times 2k plus 2. That clearly goes to 0 as k goes to infinity, no matter what x is, as long as it's fixed. And so this series actually converges for all values of x.